This is my presentation on the desalination of water using molybdenum disulfide. Water shortages and drought create disaster all over the world, with drought killing over 20,000 people every year. The effects on agriculture cause starvation as well as having a knock-on effect in the Western world. Seawater, however, is in abundant supply, but it isn't drinkable due to the high salt concentrations. Thus, finding a viable way to desalinate the water, removing the salt, could provide a solution to this problem. To outline my presentation, I will be discussing three methods of desalination, how they are overcoming the problems faced with current methods, and which is the most successful. Currently, desalination methods use reverse osmosis. In the diagram, it shows two tanks separated by a semi-permeable membrane, allowing water to diffuse through. Normal osmosis is where water flows from the side that has lower concentration of salt to the higher concentration side. However, the reverse osmosis method uses pressure to reverse the flow of water, making the saline solution more salty. The membrane is made of three layers: the polyester support base, a polysulfone layer which strengthens the very thin polyamide layer, and then the polyamide layer, which is porous and filters the solution by only allowing molecules of water to flow through the holes in the membrane, leaving behind the chemicals and bacteria in the water. One solution posed is the usage of nanometer-thick sheet of molybdenum disulfide, riddled with tiny holes called nanopores. The molybdenum disulfide is made of molybdenum atoms sandwiched between two sheets of sulfur atoms. The molybdenum in the center attracts water, then the sulfur on the outside pushes it away. Thus you don't need as much pressure as current methods, as it is pulling the water molecules in. As it is also much thinner than our current methods, it requires even less pressure to push the water through, making it highly energy efficient. This makes it a very cheap material. Thus, it is also a very robust material, so even a very thin sheet can hold up against the pressures required. Another new method that has been created is the use of graphene. This method works by poking holes in the mesh that are just the right size so that water molecules can penetrate. To create these holes, the graphene sheet is exposed to oxygen plasma, knocking out carbon atoms, creating pores in the lattice. Salt ions are larger than the water molecules and cannot pass through the holes in the membrane. It is one atom thick, yet flexible and strong. Thus it requires less pressure than our current methods. This again makes it relatively cheap. However, molybdenum disulfide is 70% more efficient than graphene methods. Another problem faced by current methods is biofouling. This is where biofilm forms on the surface of the membrane. Biofilm are microorganisms that block up the pores of the membrane. Sodium hypochlorite is used to remove this film, but damages the membrane, causing degradation of the polyamide. Scientists have found a way to produce a much more chlorine-resistant membrane. Using an organosilicon product, a compound containing silicon and carbon atoms, which form a resistance to chlorine concentrations of up to 35,000 parts per million, compared to the current 15,000 parts per million of the conventional polyamide membranes. It is also very stable at high temperatures. This means the method is potentially cheaper, as less maintenance is required, as the material won't need much replacing. To conclude, molybdenum disulfide offers the most benefits in comparison to the other solutions. The main advantages are the fact that it is lower power and a high volume of water is produced. However, biofouling hasn't been considered in the research currently, and thus further research is required. However, it could potentially be implemented into modern desalination methods. To summarize, there are various possible new technologies available in finding a solution to the problems faced by current desalination methods. Each presents its own benefits, such as cost-effectiveness or resistance to biofouling. However, the most feasible solution is the molybdenum disulfide. However, there is further research required, but it does show great potential in this area. Thank you for listening.